Hey, ladies and gentlemen, welcome to Tuesday. Happy to see you guys again. So we're going to pick up where we left off, talking about carbon, hydrogen, hydrocarbons, and all that jazz. And I'm going to also be able to explain the ring and those weird line drawings I was making yesterday. First, we need a couple notes. So grab a piece of paper and let's start. First off, a statement of fact. Most elements, let's think, I don't know, nitrogen, iodine, argon, iron, can form a few thousand compounds. Okay? Most elements can form a few thousand different compounds. So if you were to list out every single version of combinations, most of them can make a couple thousand. Carbon can make over, you ready for this? 50 million. What the heck? Most elements can form a few thousand compounds. Carbon can form over 50 million. What the heck is going on there? Carbon's a special element. Why can carbon make over 50 million? Carbon's super stable, guys. Carbon's super stable. Why is it super stable? Carbon's super stable because, number one, carbon has 4 valence electrons, and that ends up looking like that. Carbon has 4 valence electrons, and it needs 4 more to make an octet. Basically, when they have 8. That's good for stability because that means it can combine with a lot of things, maybe one on each side, make it really balanced. It's not super electronegative. It's nice and in the middle. So that's the first reason it's super stable. Number two, carbon forms strong chemical bonds with other carbons. There's a lot of elements that don't play nice with each other. Yesterday I drew this as part of our lesson. As you'll remember, you don't have to write this. Do either of these look super happy? They both have a charge on them. Carbon doesn't have to do that. Carbon can just stay happy and neutral. So carbons work well with other carbons, and they string together a lot. Last but not least, third, carbons form stable, unreactive, that's the key word here, unreactive bonds with hydrogen. Now, why is unreactive the important word there? Well, if something's highly reactive, that means it's going to be pulled apart a lot. When we talked about acids and bases, right? The hydronium hydroxide, those H's were just going from left to right, leaving this thing, going to that thing. It was really, really unstable and very highly reactive. These are unreactive and they're very stable, which means once you put them together, they're probably going to stay like that. So with this stuff as our background, why carbon works so well, let's look at how it works so well. All right, so something we call skeletal formulae. So if you had an atom that was, I don't know, C double bonded with O, that's bonded with a C, with a C, with a C. This has an H, 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 this has an H. But this only has one H because there are 4 bonds there. Is this fun to draw out? No. It takes forever. Skeletal formulae is a shortcut that you use in organic chemistry to draw these, but in a lot less complicated way. So, how do you do it? Let's say this is our example, okay? 4 carbons, surrounded by H's, every carbon has 4 bonds connected to it. So step 1, once you have a big molecule like that, is to change your C's to points and then connect them with a zigzag. Now before you're like, what the heck is he talking about? Let me show you. So how many C's do I have? 4. So I'm going to draw my 4 C's as zigzags and connect them. So C1, C2, C3, C4. So zigzag, right? So instead of C's, we're just going to draw points and connect them. And then we still have our H's, right? So we had an H here, 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 and H here. Okay, well, we still did a lot of work, so there has to be another step, right? It's got to be shorter. Pause it if you need to finish copying that, please. Number 2, ignore your H's. Woo, because we can assume they're there. In nature, these carbons are almost always bonded with hydrogens, so we can assume that they're there. So we're just going to delete all the hydrogens from the picture. And we end up with a picture that looks like this. And scientifically, this and this are the exact same thing. Every point is a carbon, and all the hydrogens are assumed. Now, what happens if you have something that's not carbon or hydrogen? That's where step 3 comes into play. You keep in all the atoms that aren't C or H. Well, the H's that are connected to a C. So if it's not a C or an H, you're going to still write the letter in. Let me give you an example. Let's say we had C bonded with C, double bonded with O. And this would have an H. This would have an H, an H, and an H. Okay? So if we had CCO surrounded by H's, how we would draw this is, well, the C and the C become 0.1 and 0.2. This is double bonded with an O, so we would draw a double bond to an O, and then ignore the H's. And that's it. All the carbons become a line, and then we leave in the letter that's connected to. Now don't worry, I'm going to give more examples and there's going to be more practice if this is causing your head to spin a little bit. Alright, so some examples. I only want you to put 1 and 3 in your notes, okay? Because you should be okay with just watching the other ones. So for number 1, we have 5 carbons in a row with a bunch of hydrogens around it. Every carbon is going to become a little point, and they're all on a zigzag. 1, 2, 3, 4, 5. Alright, and then I connect them. I delete all the hydrogens. That's the skeletal formulae. Alright, pause it if you need to copy that. It's that quick. So for number 2, I have a carbon with hydrogens bonded to a carbon, triple bonded to a carbon, then bonded to one more carbon. So I have 4 carbons. So an important note to make in your notes, please, is you know how you do zigzagging up and down? The reason for that is because it's very hard to tell the difference between your carbons if they're in a straight line. So you go up and down to show that there's different carbons, right? So you can tell the difference between these lines. Because if it was just one straight line, I don't know how many carbons, there could be 50 there. Who knows? But for this one, number 2, I have 4 carbons. First carbon, second carbon. I have a triple bond to another carbon. Now I can tell the difference between a single bond and a triple bond, so I don't actually have to change direction here. I can keep going. And then I have a single bond after that. Do you see how I can tell there's a bond, a triple bond, and a bond? I didn't need to go like this. That's just cluttered. This is better because I can see bond, bond, bond. Whereas if I did it with the first problem, bond, it's hard to tell which one's where because there's no different bonds. So for this one, my answer would actually be just in a straight line. Let's look at number 3. Whoa, there's that ugly sucker again. And yes, I do want you to copy this down. So pause the video if you need to copy this. It's 6 carbons in a circle, each carbon having 2 hydrogens bonded to it. I'm going to be looking for that in your notes. This is important. This is one of the biggest structures you see in chemistry. And these are all single bonds, by the way. So I have 6 carbons in a hexagon. So I'm going to redraw those. and they're all zigging and zagging, so you can tell the difference. I delete all the hydrogens, and that's it. There's nothing else interesting here. Last one, number 4, introduces something novel. We have an O here and an N, so we're probably going to have to look at our rules today. How many carbons do we have, though? 1, 2, 3, 4, 5 carbons, all single bonds, so we're going to need to tell the difference between those. So we're going to have to zigzag. 1, 2, 3, 4, 5. Okay. What's at the end here? It's not another carbon, it's a nitrogen. So I'm going to need to draw a bond to a nitrogen at the end there. And on my second carbon, I have a double bond to oxygen. So I'm going to need to draw that too. Now I have hydrogens here. I can delete all these hydrogens connected to carbons, but I made a very specific note in our notes. You keep the H's that aren't connected to C. These H's are connected to nitrogen, so I would still have to draw those. So I found this website while I was researching this stuff, and it really shows this nicely. So check this out. You have a chain of 5 carbons, right, all surrounded by hydrogens. And they said if you draw those in a straight line, that's incorrect because it's not clear. You don't know how many carbons are there. So that's why you do a zigzag. So you have 1, 2, 3, 4, 5 carbons. The idea is if you had this, you could turn it back into this. On their second example, they had 4 carbons, all surrounded by hydrogens. They said the mistake there would be to draw it like this and draw in all the bonds with hydrogens. That's a mistake because we ignore the hydrogens connected to carbons. So instead you'd have carbon, 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 carbon. Their last example was they had an oxygen connected with a hydrogen, then 3 carbons. One of those carbons had an oxygen on it, and then you had a nitrogen with some hydrogens. This one's a messy. So they said the mistake would be that you ignore the hydrogens connected to oxygen and nitrogen. Because remember, we keep the hydrogens that are not connected to carbon, but we delete the ones that are connected to carbon. So the correct way to put it would be to keep the O and the H together, then to draw your 3 carbons, so zig, zag, zig, and then that last one connects to a nitrogen, and you keep the hydrogens because they're not connected to a carbon, and you have to draw the double bond with the oxygen in, or with that first carbon. I've got a short worksheet for you guys on Google Classroom to try to hone these skills because this is a bit of a weird topic. But don't worry, if you're lost, we're talking about it again tomorrow. So hopefully tomorrow we can treat some of the problems you're facing. Don't forget, I do have a Zoom meeting from 3 to 5. If you're struggling with this, I can help you through your homework. Bye.